Hello, and welcome to a second video that we've got going on for motion. The first video, which you might recall, we were taking a look at a little video. Video looked like this, and we plotted the position and the time for the ball as it rolled across a flat surface. And using that information, we were able to make a motion diagram, and then ultimately we were able to make a position versus time graph here. And it came across as pretty much a straight line. There was a little variance there, but we could have re-recorded some data if we thought that we had a problem. But we didn't, because we were just doing this more conceptual. But we saw that something moving at what seemed to be a constant speed, or at least relatively constant speed, produced a nice straight line graph. And I asked you at the end, I gave you a follow-up question to consider how would the graph of an object that's moving faster look, or moving slower. And I think it's important to really consider that, because how a graph looks is very, very useful to us. So we can make some assumptions based upon how steep a graph is or how low slope a graph is. And so let's take a little bit of time here to consider that. If something were going faster, we've got two different variables we're looking at, time and position. So there's two different ways that we can approach a comparison of what the graph should look like. Let's go ahead and pick let's pick a position. Let's say that I wanted to compare a fast-moving object to a slow-moving object for how long it takes to get to the position 20. So if I got a little dotted line there, it's pretty straight across. If I read my graph, my best fit line for my graph, 20 centimeters should be somewhere around 0.33, 0.34. Like, we can kind of interpolate data to figure out what time the ball that was rolling should have taken to travel 20 centimeters. So here's my question now. If an object were moving faster, which way would the time go? That's where we are for our point, the ball that we had. Would it take more time or less time for a faster object to get to 20 centimeters? Consider that. Now, hopefully you would say that it would take less time to go the same distance. That's if we hold one variable constant, the position, then we can take a look at the time as a variable. Would it be greater or less than for a faster object? And it should be less. We should take less time to go the same distance if we're moving quicker. So that's one way to put some sort of hypothetical data point. I'll put like a green X asterisk sort of thing there. That maybe that's where the object would go. Now, what if we took another approach? What if we held instead of the position constant and the time as a variable, what if we held time constant and looked at what the position should be? So for instance, how about I take a look at 0.2 seconds here. I apologize that this graph doesn't have the times on it. 0.1, 0.2, 0.3, 0.4, 0.5. So what if we held 0.2 seconds as our constant? So in 2.2 seconds of time, our ball rolled about 11 centimeters. Well, if we were going to be moving faster, should we have a position that's greater than or less than the 11 centimeters? Where should we be if we were moving faster? So hopefully you're considering that idea of like, well, in the same amount of time, should I go a greater distance or a shorter distance? It should be the greater distance, which means that we would end up with a point maybe someplace up here, put a little blue X there. But the idea you can see, hopefully, is that both of those points, both of those lie above the current line. Now I'm just kind of hypothesizing where those points would be, but they both lie above this line, and the greater the time that goes by, the greater increase in change in position we should have if we're moving faster. So if something's going faster, the line should be steeper. If something were going slower, see if I have a color for slower here. Something we're going slower, the line should be lower slope, because in that same time, it would go less distance. Or for the same change in position, it should take greater time because it's moving slower. So we would have a slower graph and we would have a faster graph. Now that is, of course, assuming that all objects are starting at the origin, 0 position, 0 time. The whole y-intercept thing is going to change things based upon where an object starts, but the steepness is going to dictate how fast it goes. So now that that's over with, let's go ahead and take a look at some very, very key important definitions that we're going to be using continuously from here on out. And then we're going to take a look also at a new video and a new graph. So the definitions that we have to kind of lock into our brains from here on out are position, distance, and displacement. Those are the where sort of questions. Position is the location of an object relative to some origin. It's measured in centimeters, meters, miles, whatever. But if you got a point you call 0, where is an object that you're interested in compared to that origin? We'll have to worry about left, right, up, down eventually, but for the time being, let's just stick to, we're talking about one-dimensional motion, so kind of forward, backward, that's all we care about. We're not dealing with 3 dimensions or anything. For distance, we're going to call that the sum of all the changes in position of an object regardless of direction. So if I've got an object, say it's this red dot, and as time goes by, I kind of move here, then I move there, then I move here, then I move really, really fast over here, and then that's where I end up. Well, the distance I've traveled is all these little green arrows. It's every step you take. Doesn't matter which way you're going, it's total number of little teeny changes in position as time goes by. Displacement, on the other hand, is just a before and after. It's initial to final. We don't care what happens in between over some time interval from beginning to end. We just care about what the overall change in position is. So where that green arrow represents green arrows represent the distance, total distance, the blue arrow represents the overall displacement. So a common thing to talk about is if you're doing, let's say, track and field sort of stuff, and you start at the starting line, you go around the track once, you have a total distance of, say, 400 meters, whatever the size of the track is, but your displacement is 0 because you're back where you started. Now, these two definitions come in handy when we're talking about the difference between average speed and average velocity. I'm going to go ahead and delete that little track thing because I want to write some equations here. Average speed is defined as the total distance divided by the time interval that it took. So if I go through this green arrow here, if it takes me 5 seconds, I take the total distance traveled divided by 5 seconds. That gives me my average speed. Now I'm going to write that here as speed. Actually, I should write the word AVG in front of it. Average speed equals distance divided by time. Now I'm not going to use any sort of equation variables for that because we're going to reserve that for the average velocity. So because average velocity is one measurement of displacement divided by the time interval, we're going to go ahead and introduce some variables for it. And that would be the lowercase v to represent velocity with a bar over the top to represent average. Now, that looks kind of like a tilde. Sorry, no accent marks here. So a little bar over the top to represent average. Sometimes in mathematics that means a mean value, like in statistics. So we're looking at the average velocity, not at any given moment, but just on average, how fast are you going? That would be equal to delta x, where we use x for position. Delta meaning change, so that's a change in position, divided by delta t, which is the time interval. And that's going to be our equation for average velocity. Oftentimes, if we're asked to calculate average speed, we'll just write the equation the same way, and we'll replace the delta x with distance, although technically distance and displacement are not the same thing. So this equation is reserved for average velocity. If we're going to talk about speed, we'll generally write out the word speed. So What we want to do next is kind of get into the idea of acceleration. But let's kind of take a quick look back and see if we can calculate what the average velocity is for the graph that we just had. So delta x over delta t. Now we've got a whole bunch of numbers here and we've got some lines and stuff. So I'm going to go ahead and erase a bunch of that because it's so messy. Okay, so for our graph, we can find the average velocity of that ball, v bar, is equal to delta x over delta t. And, well, it's a formula. We got to pick some points so we can find the delta. Essentially, we can expand that delta and it'll be some final x position minus some initial x position. We use f and I for final and initial, divided by some change in time. We write that as tf minus ti. Now, generally speaking, for times, we don't always write the f and the I there. We just put a delta t because we're usually told what the time is. We very rarely have time points unless we're doing graphs. But you might look at this and say, well, gee, this is looking really similar to something I've seen before. I'm trying to get a value and I've got a delta over a delta. It should start to look a lot like the slope formula. And since we just said that a steep slope meant something was going fast, that would be greater velocity. A low slope would mean something going slow, which would be a slow velocity. So the slope of our graph is actually going to give us the velocity of the object, the average velocity. So we can go ahead and pick a couple of data points here. I'm going to pick two that look like they're kind of close to the best fit line. Whenever you draw a best fit line, you want to find points that are closest to it. So I'm going to pick those two there. And essentially this equation is just finding the slope between them. So you got to rise and you got to run. And our data points there, we have time 0.3 and position 16.5. And for first we have 0, 0, so our calculation here is going to be lickety-split pretty quick here. We're just going to have our final position 16.5 minus 0 is the original position divided by 0.3 minus 0. And we have our average velocity. Sorry, my V's, my cursive V's start to look a lot like U's at some point. We would have 16.5 over 0.3. That's supposed to be seconds. And if we calculate that out, we get a whopping 55 centimeters per second. And that's how we'll write the units for any sort of velocity or speed. It's always a distance divided by a time. So centimeters per second, meters per second, miles per hour, like there's a whole lot of different ways we can write that. Now, generally speaking, centimeters per second is not our standard unit. We like things in meters because we generally talk about things that are moving great distances. So if we wanted to, we could convert that 16.5 centimeters into meters initially and then finish the calculation. So if we did that, 16.5 centimeters, where we have 100 centimeters for every 1 meter, would be equal to 0.165 meters. And if we recalculate, we'd have 0.165 meters divided by 0.3 seconds, which would give us 0.55 meters per second. Now, that doesn't necessarily mean anything to you, it's just a number, but it's something that we can use for comparisons later. Now, we're going to take a pause in this video because it's about 15 minutes long, and then pick up part 2, where we're going to talk about what happens when an object is accelerating.